Hey everyone, in this video we're going to be looking at the big ideas for section 8.1. So there's actually quite a bit that we need to cover here, so let's dig into this. The first thing that we want to talk about is what is a point estimate? I think it's important that we use proper vocabulary. So a point estimate is basically this. It is a statistic that provides a reasonable guess for a parameter, a population parameter. And most of the time, what we're going to see is our point estimate is going to end up being a sample mean or a sample proportion. Eventually, we're going to be looking at the difference between two sample means and the difference between two sample proportions. But that statistic that we start with, and remember, a statistic comes from a sample, it is used to estimate and give a reasonable guess for a population parameter. That is called our point estimate. So once again, p hat is our statistic that we use to estimate P, the population proportion, and X bar, which is our sample mean, is used to estimate mu, which is our population mean. Oops, let me draw that again, make that look a little bit better. There we go. All right, so knowing that, there's a few things that we need to know concerning confidence intervals. We should know that a confidence interval, let's get this down, confidence interval looks like this. Every single confidence interval is going to be a point estimate plus or minus a margin of error. Every single confidence interval that we create is going to follow this particular pattern. We're going to start with our point estimate, and we're going to add and subtract a margin of error to create this interval. And these intervals may end up looking, it's just going to have two numbers. And we'll just for right now call them A, excuse me, A and B. So if A to B, whatever those two numbers be, whatever those two numbers are, if that's our interval, then there's a couple other things that we can know just through algebra. Our point estimate is going to be equal to A plus B divided by 2. So if you know the interval and you're asked to find the point estimate, just add the two numbers together and divide by 2, and that'll get you right back into the middle. The average of these two numbers is the point estimate. And then the other thing that we can do is this. Our margin of error could be found by taking B minus A. In other words, the range of your interval, you take the bigger number minus the smaller number, and divide that by 2. And that's going to give you your margin of error. Okay, so this is just the basics when it comes to a confidence interval. Well, another thing that we're going to be asked to do when we are working with confidence intervals is we are going to be asked to interpret a confidence interval. So this is going to take a little bit longer, so I'm going to type this one in. But when we are asked to interpret a confidence interval, we should just follow this pattern and follow this model. We would say this: we are blank percent confident that the interval from blank to blank captures the true, and then this is where we have to fill in the blank with context, captures the true whatever. And that whatever is our parameter in context. So if we're trying to estimate the true proportion of left-handed students at Mason High School, then we might say something like, we are 95% confident that the interval from 25% to 29% captures the true proportion of left-handed students at Mason High School. Okay, so this pattern right here is a pattern that we're going to follow every single time we interpret a confidence interval. Okay, so that is important. All right, another thing that we need to talk about is making decisions with confidence intervals. Okay, so if we type this in like this, making decisions. Now, what we're basically saying is this. A confidence interval gives us a confidence interval gives us a list of plausible values for whatever we are trying to estimate. Okay, so if our interval, let's go back to just left-handed students at Mason High School. Let's say that our interval, our confidence interval went from 0.15 to 0.21. Okay, so 15% to 21%. Okay, this gives us a list of all the plausible values for the proportion of left-handed students at Mason High School. So if I were to ask you, if I were to make a claim like this, Mr. Mays claims that 25% of the students at Mason High School are left-handed. Does this interval support this claim over here? Does this interval that we've created support that claim? Well, no, it doesn't. Okay, this interval is estimating that 15 to 21% will capture the true proportion of students at Mason High School that are left-handed. If I claim that it's 25%, this interval, we might not know if it's right or wrong, but this interval does not support this claim over here. So that's something that you're going to be using confidence intervals for just a little bit. It's not going to be the main thing that we do with confidence intervals. The main purpose of a confidence interval is just to make an estimate and give us a list of plausible values. But if you're asked if a particular confidence interval supports a particular claim, just look to see if that claimed value is inside of your confidence interval. So another thing that we're going to be asked to do is interpreting a confidence level. And hopefully we've been able to take the time in class to kind of show this diagram right here. And what does it mean to be 95% confident? Or what does it mean to be 90% confident or 99% confident? Well, the way that we would interpret it is right here. If we make many, let's just go with 95%. If we make many 95% confidence intervals, we can expect about 95% of those intervals to capture the true whatever that parameter is that we are trying to estimate. So if we look at this picture over here, the true parameter is right here, this green line right there. And so all of these are confidence intervals that have been created. There was a sample that was collected, and then we did the math, and we created each one of these confidence intervals. And every every sample is going to give us a different interval because the point estimates are slightly different. Well, what we can see is that it's not going to be exactly 95% in this particular example, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There's 18 intervals that have been created. And of those 18, 16 out of the 18 capture the true parameter. All of these intervals that are in black capture the true parameter that's right here in this vertical green line. There's only two, this one right here and this one right here, that do not capture the true parameter. And that's what it means to be 95% confident or 99% confident. If we were to create many 95% confidence intervals, then we would expect about 95% of all those intervals to capture the true parameter of whatever we are trying to estimate. That's what the confidence level means, okay? So there's a couple other little things that we want to talk about when it comes to margin of error. And that is this: what affects the margin of error? What could change our margin of error? Well, here's one thing. If the confidence level goes up and everything else stays the same, then the margin of error is also going to go up. So if we change our confidence level from 95% up to 99%, what's going to happen is these intervals over here are going to get larger, okay? Because the margin of error is going to increase. Now, another thing that affects the margin of error is our sample size. But in this case, if the sample size goes up, the margin of error goes down. So if we increase our sample size, the margin of error is going to get smaller. And that's because of the standard deviation or the standard error, which is a part of the margin of error. Now, there's one last thing about margin of error that we want to know, and that is, or we need to know, and that is that margin of error never accounts for bias, okay? Margin of error is just a calculation. If you collect your data in such a way that leads to a particular type of bias, whether it's response bias or voluntary response bias or undercoverage or any other type of bias, margin of error is never going to account for that. It's never going to be like the margin of error is not determined by any type of bias that may show up in the way that you collect your data. So keep that in mind. When we create a confidence interval, one of the things that we have to do is we have to check some conditions. We've talked about these conditions in class, but let's get them into our big ideas. The first thing is the randomization condition. We have to collect a sample randomly in order for our sample to represent the population. If you don't collect a random sample, then your sample might not represent the population, and then you shouldn't be using it. The second condition that we have to check is called the 10% condition. And the 10% condition says that our sample size must be less than 10% of our population size. Now, lots of times we won't know what our population size is, but common sense should tell us that our sample size is going to be less than 10% of our population size. The last condition that we should check when we're working with a confidence interval for a proportion is called large counts. And so for proportions, we need to check n times p, and this should say n times p hat, and n times 1 minus p hat. And the reason why we have to multiply n times p hat is because we don't know what p is. The whole purpose of a confidence interval is to estimate what p is. So if we don't know what p is, the best thing that we can do is multiply n times p hat and n times 1 minus p hat. And as long as we get at least 10 for both of those products, then this condition is satisfied. And if it's satisfied, then we are assured that our sampling distribution that we're trying to use is going to be approximately normal. So let's talk about critical values real quick. Our critical value is this Z star, and Z star is a part of our formula for a confidence interval for estimating a proportion. The most common critical values are based off of the most common confidence levels. So a 90% confidence level is going to lead us to a Z star of 1.645. 95% confidence level leads us to a Z star of 1.960, and a 99% confidence level leads us to a critical value of 2.576. Now you can use, if you get any confidence level that is different than these three, you can just draw the picture and use inverse norm to help you find the Z-score that cuts off that particular value, okay? The last thing that we want to talk about is our formula for a confidence interval. So our formula for a confidence interval for a proportion is going to be this. And actually, this is a 1 proportion confidence interval. And our formula looks like this. It's p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by our sample size. Now there's one little note that I want to put on this, and that is this part right here. This is very, very similar to what we have been calling our standard deviation for a sampling distribution. But when we were working just with sampling distributions, instead of using p hat right here and right here, we were using p. But once you start using p hat, because that's the only possible value you have, this would be called not standard deviation, but this would be called standard error. So there's a little bit of a vocabulary that you need to remember here. We don't know what the parameter is, so we are using p hat to estimate that parameter, which means we're also using p hat to estimate the standard deviation of the sampling distribution. And so we don't really want to call this standard deviation of the sampling distribution because we're not using p, we're using what we think p is close to in p hat. So technically this is called standard error. That was a lot for our big ideas for this particular section, but we had to cram a couple of lessons in together, and hopefully this helps you understand confidence intervals a little bit better, and hopefully you have a great day.